our 10 digits here, but then we run out of digits. We don't have numbers of over 9, or I should say digits over 9. We don't. We have to have something that takes a single space. So now we start with letters, like this. No, 8 bits should not be 3 X's. When we represent an 8-bit number in hexadecimal, it's remember, A, B, C, D, E, F. Well, the problem is there's only 26 letters in the alphabet. So if R was 32, where do I get the extra 16 letters from? Well, I can do that, but now we have a human problem. And the human problem is, okay, quickly, someone, as fast as you can. Where is R in the alphabet? What's its position? Someone says, I don't know. But if I asked you where's position, okay, a couple people got it. It's 18. But if I ask you, well, where is position? Where is A positioned? What would everyone say? 1. Sure. And where is B? 2. Where is C? 3. So the first few letters of the alphabet, we know the position. We can visualize it in our brain. But when I start saying things like R, V, you guys don't know where it is. I don't know where it is. How do I know where R is? Because I know the hexadecimal representation in my head, because I use it all the time. Okay, hopefully all of you know that Z is the 26th letter in the alphabet, and that's about as far as it goes. And I wouldn't expect more from you. So can we do base 32? Sure, we can. But the problem is human problems get in the way, and we can't reliably positionally know where those letters are. So we would end up creating more problems. So the first 6 letters of the alphabet, I think you guys know the position of those letters. Okay, so again, this is every 4 bits of binary. I'll have an example on the next slide. So with this, so rather than writing, for example, 8 binary 1s and 0s, I only need 2 hexadecimal digits. Or rather than writing 16 1s and 0s, I only need 4 hexadecimal digits. Or rather than writing 32 1s and 0s, I only need 8 hexadecimal digits. So it's easier for us as humans to kind of process that information. So again, here's an example of just switching between bases. And okay, someone just has the question, can you elaborate why 8 bits is 2 X's? Okay, so every 4 bits of binary is 1 hexadecimal value because R is 16. And I'll show an example again on the next slide. So if every 4 bits of binary is 1 hexadecimal digit, so if I have an 8-bit number, I should require 2 hexadecimal digits. Okay, so again over here, let's just start out with the hexadecimal one first. So here's my hexadecimal value. Now, again, it's all bunched up together, and it's very difficult for me to find out where is a particular digit. I would have to count from the beginning. And again, our human brains do funny things. If these were all zeros and I had to count a position, sometimes when I'm counting, if I'm not using my finger literally to keep track of things, my brain might, my eyes will actually kind of overlap the digits when they're focusing. This is something that can easily happen. So it's best to kind of like, okay, let's group everything into groups of 4 bits. And we always start this at the radix point. So again, if you don't see a decimal anywhere in the number, there is a decimal there, right? Just like when we write out any decimal number, there's always a decimal. We just don't always write it down. So starting from here, we group into groups of 4. So I just recopied this going into groups of 4, and this is the number I have. Right? And then I take each of those groups of 4, and this is going to be only one of 16 possibilities. So this is a 2, this is a 3, this is an E, and so on and so forth. Now we did most of this stuff in DLD1, so I'm not going to cover it, over again. And the same thing can be said for octal. We start at the radix point, but we go in every group of 3 digits, right? So we can easily convert back and forth between octal, hexadecimal, and binary. Now, what if I don't have enough numbers here, enough digits up here? I just pad them with zeros if that's the situation. Okay. So it's much easier to see, can I read this number as a human as opposed to this number? Now, of course, a circuit, it can't really do this because it only operates on 2 states, every input. So the whole 1s and 0s thing makes a whole lot of sense for a circuit to understand. Again, it doesn't just look at this and say, oh, I know what that is. I mean, every bit goes into a particular position. So we don't just arbitrarily give it ones and zeros. They have to be aligned correctly. But it can certainly take this 0 and bring it into a MOSFET and do something, you know, turn it on and off or whatever it does. But it can't take a 2 or 3 or something. Again, this is just for our benefit. So we can write things out easier and we can read things easier. Okay. All right. All right, now the situation may come up, okay, well, if we have unsigned numbers and signed numbers, and again, those are just integers, what do we do with floating point or real numbers? So real numbers is a particular problem. How do we represent numbers with decimal points? I mean, most of our calculations are done that way. We don't really sit back and say, okay, how do I do everything with integer math? So we have a method of, again, a standardized method on how we store numbers, real numbers in computers. Now, again, we can kind of vary on this a little bit, but this is basically the way it works. So essentially, we have some number y that we raise to some power of 2 to some exponent. So we record the exponent itself, the base number itself, and the sign. So the sign is either -1 or 1. Y is, again, this is the mathematical term, the mantissa, and E is the exponent. And Y is always greater than or equal to 1, but less than 2. So we always want to make sure that Y is what we would say normalized. So it's always between 1 and 2. Now, if Y is larger than 2, then I could take Y and divide it by 2 and increase E to kind of balance that. So we can always change the exponent to compensate for normalizing Y. Okay, and there's a good reason for this. Now, it turns out there's only one number that kind of breaks this rule. X is the actual representation of the number you want to represent once I apply these 3 inputs. So my floating point number, so whatever real number I want to represent X, I have to break it into these 3 parts: the sign, the mantissa, and the exponent. Well, these will be represented in ones and zeros in some way, shape, or form. Okay, but there is one number that this won't work out with. When I say Y is between 1 and 2, there's only one number that this will never work out with. There's only one number in the world. It is 0. 0 is not between 1 and 2, and no matter what exponent I raise it to, any number of 1, between 1 and 2 to any exponent of 2 I raise it to, will never be 0. It just doesn't happen. Okay, so it turns out for real numbers, 0 is a special case. And again, this kind of slows things down a little bit. So we, again, have more and more steps to deal with it. Okay, now I don't have a lot of information. I can give you kind of an example of floating point. Actually, I do have something here. Give me a second here to pull it up. Can I throw this together? Okay. So I created a little C program that will show me what a number looks like in floating point to a computer. So I'm going to say, show me the representation of 1. Okay, so here's all the bits. This is the decimal value, so 1.0000. So we have up to 15 decimal places. So this is what we call a double. So here's the hexadecimal digits. There's all 64 bits. A double floating point number is 64 bits. Here's the sign. So we only have 2 states for the sign. So a 0 is for positive numbers, a 1 is for negative numbers. Here's the exponent, but with an offset of 127. And here is the mantissa. Now you don't see the 1 anywhere because we hide the first 1. Because 0 is a special case, every other number in the world is always going to have a 1 somewhere in it. It's always going to start with a 1. So it's going to be 1 point something. It's always going to be 1 point something, as long as it's not 0. So let's just drop that 1. What do we need it for? Why do I need to store something that's always going to be a 1? So we drop it. So you can kind of imagine that there's a 1 here, but we just don't show it. Now, if I show -1, for example, you'll see the exact same number, exact same everything, except the sign bit is a 1, implying it's negative. If I ask for 3, I'll just go back to positive. We'll see that first leading 1. Now, the binary representation for 3 is 1, 1, and that's it. Here, again, we don't have that first 1. So there is the second 1 and all the zeros that would be after it. Again, there's an infinite number of zeros after it. However, you'll notice that the exponent went up 1. Because I'm not representing it as 3, I'm representing it as 1.5 times 2 to the 1. So the exponent has increased. Now again, the exponent, the base exponent is 127. Oh, I'm sorry, not 127. In this case, it's 1023 actually. Okay, but again, this just to give you an idea of how it works. Now the nice part about it is that we can have very large numbers. So if I say 1 plus e to the 40, well, I guess I don't have it do that correctly, do I? I think I just have to say 1e40. There we go. So that's a big number. That's a lot of digits. But I can't have a 40-bit number. Let me just pull up the Windows calculator here. I'll go to programmer mode just so we can see. See, there's a 64-bit number. And if I say 1 in decimal with 40 zeros at the end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, it won't let me do more than 20 digits. So using integers, I can't represent a number with 64 bits that ends up giving me a decimal number with more than, well, 20 digits. But in floating point, I can. But you'll notice something. I said 1e40. So there's the 1. And what is this? What's all this stuff? I didn't put that there, did I? Where'd it come from? So what you'll see is I have about 16 digits of precision here, but then everything after that, it's essentially garbage. It's just calculation error. So I don't have enough space in that 64 bits to represent all those digits. But what I do have is I can increase the range, or what we say the dynamic range. So these digits here, the mantissa is only describing this. Everything else after this, the computer's kind of making up to make the number look, well, I don't want to say normal, but it's just, these are just calculation errors in terms of saying, okay, we'll print out this number. The nice thing about this is when I have very large numbers and very small numbers, adding small numbers won't make a lot of difference. It only adds like the large numbers together. Again, we have to make a compromise on storage. I only have 64 bits to hold this number. This is as much information as I can store in terms of precision, right? So as long as I add numbers that are roughly around this magnitude, it'll make a difference. But numbers that aren't anywhere near the magnitude, or 16 orders of magnitude less in this particular case. So what's 16 times? Well, that's 10 to the 16 times smaller. I just kind of ignore. I throw them away. All right? So it's just like saying, if you were a billionaire, would you be concerned about losing a cent on a bank transaction? You wouldn't be concerned. What does a cent mean to your overall net worth? This is way worse. I mean, a billionaire, you'd be at this point here. Let's see, 9 zeros. Okay, this is like, this is like 100,000th of a cent. Would you care? So we do the same thing with computers. We want to be able to represent large numbers, but we don't necessarily need to have a lot of precision for as large as the numbers can get. So after 16 decimal places, we just throw away that stuff. Okay, so again, if I ask a computer, add 1 to this number, it's not going to do anything. So if I made this a 3, it can't accommodate for the storage of that number. But then again, is adding 1 to this number going to be significant? So for most applications, it's not. But for some applications, it could very well be. So if that's the case, we have to do math differently. It's unlikely if I do this would it show a different number. It's not necessarily random. There's an algorithm to it. I should be more particular. So the algorithm is just saying, I have nothing left. What do I have left after this? There might be a certain procedure for doing it. The way these numbers are stored, there's a standardization on it. It's a very large document, probably hundreds of pages, that outlines how to deal with that and how to deal with rounding and other particular issues that come up. For example, if I made this a 3, that's going to change everything about the number. So we'll see these numbers are all different. But if I make it a 2, they might look different, but they're probably just all multiplied by 2. So yeah, this is just this multiplied by 2. Again, I can't necessarily get into all the details of why that happens. Okay. Now, again, 64 bits, we're making a compromise here, right? So I'm saying I'm getting 16 digits of precision, and I'm using 64 bits to hold that. There's another one, another standardization. This is what we call a double real number, in the sense that it takes double the storage. The single precision, as we call it, only uses 32 bits, and it only has 7 digits of accuracy before it starts getting into this situation where it can't store anything. So depending on what you are willing to compromise, you get different performance. So here's the standardization for floating point. So single and double, you guys have heard of these terms in C perhaps. Well, you've probably heard single is called float sometimes. Other languages say single. So 4 bytes to hold the information. So we have 7 digits of precision, which is roughly 24 bits. Again, that first bit, that first one is thrown away because we don't need to store it. Whereas in double precision, we have 16 digits, so 53 bits to hold the information. And this is roughly the range of numbers we can support. Now, again, the numbers look large. Again, this is its dynamic range, but individually, there's only 7 digits of precision. So if I'm using a single representation, and I take 1 billion and I add it to 1, the answer is going to be 1 billion. It's not going to be 1,000,000,001 because I don't have the space to hold that number. Now, again, that might be fine for your application, but for other applications, it may not be. So for scientific computing, we don't use this. In fact, for scientific computing, we don't even use this. We have to go further. There's something called a quad, or not a double-double, but it's called a quad, which means 3 of these, or 4 of these, sorry. But it's much, much slower. So when we want better performance in terms of more accuracy, it's going to cost us in some way. It's going to cost us in space, and it's going to cost us in speed. So if you have any gamers out there and you're playing a game and it's, showing your screen and it's updating all the, the 3D stuff, when they do those calculations, they're using single precision math. Because you're just playing a game, are you going to notice if there's a problem? Are you going to notice that there's an inaccuracy somewhere? They're not going to use this because it's too slow, right? They're going to get half the performance and it's going to cost twice as much money. Who wants to pay for that? Nobody. Now, interestingly enough, on your cell phone, for example, it's a 3D system. Equations about the last slide. I can probably give you a couple examples. We can just kind of do them here. I'll see about doing that soon, but let me just get my one point across. So on your desktop, it's using single precision math to do the 3D rendering on your games. On your phone, that's too expensive in the sense of the time it takes. So there's something called a half precision floating point, where they only use 2 bytes. So it has even fewer digits of precision, but again, because your phone screen is so small, the power is limited, you won't actually notice it unless you know what to look for. Okay, again, you have to have kind of a trained eye and you have to be aware of these things. So your phone is actually using only 2 bytes to do those calculations. But it's good enough. So when you're playing those games, that's one way they ended up actually making your phone kind of keep up. If you've seen mobile computing mobile gaming is, well, I don't want to say it's decent, but it's okay. It's because they're doing less computational work, but it still looks okay. But if you look at it on a large screen, if you took your phone screen and kind of like put it on a large, 80-inch HD TV or something, and you actually looked at the picture, you would start noticing, oh, well, that doesn't look quite right, and that doesn't look quite right, but it's good enough, right? Again, you're just gaming on a phone. All right, so as far as more examples, hold on, I just want to see, oh yeah. So again, here it was just a more of an explanation of what's happening here. Just how the information is stored. So again, we have the 1 bit for the sign, the absolute integer values for the mantissa. Basically, it's just an integer number, but again, it's in a representation of 1 point something, where we drop the first one. So we actually have a 24-bit number for single or a 53-bit number for double, but we drop that first one. 0, again, is a special case. Okay, let me just kind of go back here. So the special case of 0 is if all of the bits are 0, then the number is 0. That's the special case. But any other thing, and there's actually some other ones, if I can just see this works. We have a representation for infinity. We have a representation for negative infinity. We have a representation for, does anyone know what nan means? Not a number. It means somehow the calculation just didn't work out. There was some problem. So it's just a way of telling us that it's kind of like an error. I wonder if we have negative not a number? No, just not, only not a number. Okay, so we kind of have to have these things because we're using this stuff for like real computing, things that can affect a whole bunch of things. But we do have to be aware of the limitations. So this is one way we can store it. Now, floating point comes at a relatively large cost, right? To build floating point hardware is much larger than integer stuff. Like when we did a ripple carry adder, there you go, there's your adder. A floating point adder, there's a lot of work actually that goes involved in it because of the representation of the numbers. Okay, so someone wanted an example here. Can I show you? Well, there's not much to see in terms of C. We just declare it as a float and we do whatever we want to it, right? You can add 1.1 to it or something like that. I'll see if I can pull up the whiteboard here. And we'll do something here. I should have my pen ready. Do I have my pen ready? Here we go. Okay, let me just erase that. Oops, try again. Okay, so if you give me a number, for example, someone just throw out a number, something reasonable, maybe with a decimal point. Well, 4 is too easy. Okay, 10.2. Okay, you guys have to forgive my writing here with this board. So we have to take this number and normalize it. I need it to be between 1 point something or 1 and 2. So what do I have to do to this to get it to between 1 and 2? I have to divide it. But what do I have to divide it by? Okay, so if I divide it by 8, can someone divide this number by 8 for me? So I'll divide it by 8. Or that 8 is 2 to the 3. So I'm going to get a number times. And of course, it's positive. So my sign bit would be a 0. My mantissa would be this 265. Now, this number here itself is going to be written in binary. Okay, so we're not going to get this 265, but essentially it would be written in binary, and this 3 would be written in binary. So our sign would be 0 to mean positive. Our mantissa would be 1.265, but we would drop the 1 because it's always there, and the exponent would be 3. Do you have to divide the number by a multiple of 2? Yes, it has to be a multiple of 2 because we have to represent it in an expression like this. Now, what if my number is this, 0.00349? What do I do in this case to get it normalized? That's a 3, by the way. I have to multiply by 2, right? So what do I have to multiply this by to get it in between 1 and 2? Any ideas? I don't know if multiplying by 8 is going to get it up there. Someone figure it out for me. Just keep multiplying by 2 and count how many times you did it. And then let me know the result. Okay, we could guess, or someone can actually do it. So multiplying it by 512, sorry, so 2 to the 9 is what you're saying we have to multiply it by, right? Okay, so there. And what is the number once I did it? Someone said 1.78688. So are these not equivalent? These are equivalent, right? But now, so there's my, basically my representation. Now, here's where the challenges of floating point come in, and here's where some of the simplifications are. What if I want to multiply these two numbers? What do I do? Why -9? Because I had to divide it. I had to take this number and multiply it by 2 to the 9. That's 512. For it to get between 1 and 2. So we have to normalize it. We have to get it into that space. Okay, so again, if I want to multiply these two numbers, what are the steps? You guys remember multiplying numbers with exponents? What do we do, especially when it's the same base? I simply multiply the two mantises together, and then I add the 3 and the 9, or the 3 and the -9. Now, it is possible when I do that, the multiplication or the product of the two mantises will go out of spec. In other words, they'll be greater than 2 or less than 1. So then I have to renormalize it and accommodate for the change in the exponent. But it's really not that much work. So again, why does the number have to be between 1 and 2? So when I go multiply the numbers, they're already normalized. There's another reason why. So when we want to add the numbers, the same thing happens. If I want to add these numbers, I can't simply just add the mantisses. I have to renormalize them. I have to look at the exponents and readjust everything and then add the numbers. So there's actually a lot of work into manipulating floating point numbers. And it's often why we don't want to use it if we can avoid it. We only really want to use it if we absolutely need to. Yes, so making the number between 1 and 2 is called normalization, yes. Well, in this case. The mantissa is not the exponent or the sign, it's just this number. It's the number we're going to multiply by some value of that exponent. So we're always going to use base 2 in this particular case. These numbers here, again, I'm just writing them out as base 10 just for our purposes, but we can easily convert them to binary. I'm not sure what that one, a 10-bit number? Or do you mean a base 10 number? I'm not sure. In this particular case, they're just normalized to be between 1 and 2. The same thing would happen, again, in binary. So again, if I wrote this out in binary, again, pick this number. You see this? Okay, I'll go back to, give me a moment here, just to kind of reiterate the point. And what was that number again? 1.265. Right. Okay, well, you can see it's kind of long, but I think, yes, if I wrote out 100, again, there's a little bit of a difference between doing this in binary and decimal. I just want you guys to understand the concept. But let me just pull up the calculator here. 1265 in binary. Well, it's not quite the same because of it might be dropping the first one already. There is a little bit of other little details that I'm not showing you here. Again, I don't want the whole lecture to be about this. Believe me, I could probably have a whole class on floating point itself. But it's just that idea that if I put a 1 here and take this number representation, it's going to be equivalent to this in some way. Now, again, I know this doesn't seem quite right that it does this. Again, this is software making some approximations here. So again, it's kind of giving some stuff up for performance. But I just want you guys to just be able to see, okay, well, I'm going to guess that I've lost my whiteboard. Yeah, the whiteboard's gone. PowerPoint doesn't remember the whiteboard. What do you have to know exactly? Well, again, we're not really doing tests here per se, right? So I just want you guys to understand the fact that floating point exists and there's a cost to using it. In fact, in your desktop PC, per core of your CPU, and again, you're spending hundreds of dollars on this CPU, there's generally only one floating point system. It can only do one floating point operation at once. They don't have multiple ones because they're so large. So this circuit is quite a large circuit. And if you have far more money, like the high-end systems, server grade systems will have maybe 2 floating point units in it just to increase performance. So it comes at quite an expense to deal with these numbers. But again, you know, people who write software don't want to deal with the problem of, okay, well, how can I do stuff with integers only? You know, people don't want to deal with that or trying to program it. Again, just to give you a quick example, I could say, what's 10.5, I don't know, plus 3.2? Now, there's decimals there. Do I need floating point to do this work? Do I need to know anything about real math? I could forget the decimals are there and just do normal integer math and I would get the answer and just put the decimal point at the end, right? That works just fine. So we can kind of do the same thing in computers. It's called fixed point math, where we kind of take our numbers. So what I'm essentially doing here in fixed point math is I'm taking this number here, multiplying it by 10, taking this number here, multiplying it by 10, do the addition, and then take the result and divide by 10. And I never really did any real math. When I say real, I mean real number math. Now in base 2, I don't multiply by 10 and divide by 10. In fact, I just multiply by powers of 2 and divide by powers of 2, which are no cost. That's just bit shifting and it doesn't cost us anything, right? It's the same thing here. Again, I just moved the decimal point essentially with multiplying and dividing by 2 or 10. So sometimes we do that, but you know, there's a limitation. People just don't think about doing that. So particular hardware people will do that, but a lot of software people don't want to do that. They don't want to be doing that type of work. We're trying to make things as easy as possible. So there are some computer systems out there, or CPUs, I should say, that have no support for floating point at all. In fact, when computers came out, they didn't have this at all. So they had to do something called emulation, where they kind of emulate this type of behavior. And it was extremely slow. This was an extra feature you had to pay for, and substantially, mind you. Now it's just kind of standardized, but we can still go out there and buy special CPUs that have no support for real numbers. You have to do everything with, you know, integer tricks, as we'd say. Okay, and the last type of number we have, and we did talk about this one before, and it often comes up in embedded computing, is binary coded decimal. And this is a completely different way of representing decimal numbers. With the idea that it takes very little time to do any conversion. And that's the key thing here. This is why we use binary coded decimals. It's all about minimizing conversion. Okay, so with binary coded decimal, we basically have 4 bits of binary for every decimal digit. So if I have a decimal number 1, 2, 3, it's encoded as a 1. There's the 1 in binary, right? 4 digits for the 1. There's a 2, and then there's the 3. Now, 123, this number itself, if I was to encode it directly in binary, not binary coded decimal, but just binary, I would need only 7 bits, because 2 to the 7 is 127 or 128. So if I use my standard unsigned number, I would only need 7 bits. In this particular case, I need 12. So from a storage efficiency perspective, binary coded decimal is absolutely terrible. However, it's easy to decode. So if I sat there and said, okay, where's the 1? There's the 1. Where's the 2? There's the 2. There's the 3. I can easily see the individual digits. Whereas, let me just pull up the calculator one more time. Let me write 123, and I will convert that to binary. And can anyone tell me where's the 1, the 2, and the 3? You can't see it. We have to go through a certain amount of work to extract those numbers. And you guys do remember converting from binary to decimal, the amount of work it is. It's certainly by no means trivial. So binary coded decimal has its place in terms of simplifying conversion. but it's you know, we at most we can just do some addition and subtraction with it. There's no, you know, nothing out there for multiplication and division. It's not meant for that. It's meant for simple things. So any representation in these digits, again, the hexadecimal representation of A to F is ignored. It's considered, you know, unsupported. Okay, so a great example would be the odometer on your car. If you have a digital odometer, how is that information shown to you? It just shows you this number that keeps going higher and higher and higher, right? We're just adding one to it every so often. That's all we do. So that particular circuit there is probably all done in binary coded decimal. Otherwise, how would I take that number I stored in binary and change it to a series of digits that you can understand as a human, right? It just really doesn't have a, it's a lot of work that you don't need. So binary coded decimal is quite useful there. So in embedded computing, it's something we really like. So here, I'll give you just a quick idea of this. So let's just go back to this program I wrote. So let's look at the size of this program. So this program for this computer is 7,248 bytes of code. Now there's extra code in there, debugging information, we call it, things that help us, you know, tackle problems. So if I were to get rid of that information, and I'm going to remove it right now, and look at the size, it really actually is, the code only is roughly 5 kilobytes. Now that's just the code I wrote. That's not everyone else's code of all the little things I used. So in C, there's this command called printf. And printf can print out a bunch of different numbers for us. It can do a whole bunch of things. And one of the things it does well is print out these numbers. It's what printed out this number here. Now, if I want to include all the code we needed for that, well, let me do that. I'm going to recompile my piece of code, but I'm going to ask it to include everything that's needed for it. Now let's take a look at how big it is. It went from 4 kilobytes of memory to 612 kilobytes. Now, let me strip that down just to make sure. Let me get rid of all of the debugging. It didn't do that much, so it's still roughly half a megabyte with all the supported code I needed to actually run this program. So this again is why on embedded systems, this is a large amount of code. It's far too much. So again, your phones, for example, are really just basically portable computers. They're kind of an embedded system, but you know, space isn't really so much of an issue. Whereas if I was building some type of small embedded device, that would require me to have over half a megabyte of code space, and that would be quite costly. Whereas I could just get a simple microcontroller and do BCD arithmetic, and the code could be, you know, maybe less than a kilobyte of memory. Okay, but what was easier to write? Well, if I just, you know, just wrote a piece of C code that just, you know, took the number, added 1 to it, and then used printf to show it to me or something like that. Sure, that'll work. But it's far larger than it ever needs to be. So again, this is the thing about engineering is dealing with constraints. Okay, so if I'm an odometer manufacturer and I want to get the most business I can get, then I want to make this device as cheap as possible. And the only way to do that is use the fewest parts as possible and the fewest everything, code everything. Okay. All right, so this is the end of chapter 1. Are there any pressing questions? Otherwise, I'll move on to chapter 2. Okay, all right, just bear with me for a second while I close this down. Okay, just give me a second to start it up. And I have to do this, unfortunately. Okay, all right, so So chapter 2 is basically just a review of some of the digital circuit stuff we covered already. Well, I mean, it's entirely possible I can give you an assignment that deals with conversion methods or just converting numbers. Now, as far as assignments go, you know, it's kind of a waste of time to do that because I know most of you are just going to go on some website and use it to do the conversion. So it's not really a test unless I ask you to show me all the steps involved. But we did that in DLD 1, so it's not really a thing, but I could probably give you something with floating point. It's a possibility. Again, I'm trying to think of all the things I can give you to kind of get the most out of your knowledge, since we're not physically doing any tests here. So any assignments you'll be given are, I mean, clearly they're beyond open book. They're open everything. So I can't regulate that, unfortunately. Okay, so, all right. So as I mentioned before, this is kind of a review of digital logic, not that much of a review, just like on the components and the things we use. So again, this is kind of that idea of our voltage ranges. Again, this is if we're using these voltage ranges. Again, 0 to 1, for example, in this case is considered a logic 0, whereas 2 to 3 is considered a logic 1. And this is a transition point here. Again, if I have a digital signal, it doesn't, no signal goes from 0 to 3 volts, for example, instantly. There is a time. It takes time for the signal to go up and to get all the way up there. So as long as we're kind of in between this range, we're good. We don't want to read the signal while it's transitioning. And of course, this is why we have flip-flops and synchronous circuits to kind of avoid those situations. Okay, so obviously our digital signals or our electronic circuits operate on one or more input signals to produce an output signal. So all of our signals exist as analog signals. We just interpret them as being between 0, or interpret them as being as 0 and 1s at particular intervals. So in a digital system, first of all, I translate these analog, or I should say I interpret them as a 0 or a 1. And I also, when do I read them? I only read them really at my clock periods. So whenever my clock changes is when that information is being, grabbed and used for a subsequent operation. I don't want to be looking at the output of an AND gate while it's transitioning, because what is it then? Is it a 0? Is it 1? I don't know what it's going to be. I have to wait a little longer, right? Now, as far as these voltage ranges here, things have kind of changed over time. Originally with electronics, they were between 0 and 5 volts. That was called TTL logic, which isn't technically all about voltage. There's some current involved there. So you'll often hear the term TTL compatible, which means voltage range is only. In this particular case, again, the 1 is, or a 0 is between 0 and 1, and a 1 is between 2 and 3. But again, that's just an example here. Okay, most systems today, any circuit board that you look at will be up to 3.3 volts for a 1. But when we get into your CPUs of today, the internal voltages at its fastest point could be as low as 0.9 volts or even lower. Because it takes time. So if I want to bring this signal, let's say I'm at 0 and I want to bring it up to a 3, it's going to take time to pull that signal up, right? So the way we make CPUs faster is saying, well, let's make, this is 0, but this is a 1 up here. So if I only have to pull up to about 0.9 volts, it takes me less time to get there. So it's, in a sense, it's to their advantage to do this, but there's also a risk of there being noise, right? So again, with CPUs, there's a whole variety of voltage ranges depending on what part of the circuit they're in. But this is kind of a compromise to improve performance. Now, do keep in mind, a modern day CPU would not work well in a noisy environment on its own. It has to be shielded properly. So in particular, as I mentioned before, if you're going to bring a modern PC into space, it has to be heavily shielded. That's if it works correctly at all. It's quite normal that anything that leaves our atmosphere, any type of technology, is actually older because it's less susceptible to this noise. Okay. Our atmosphere has a lot of radiation eliminating factors in it, right? So a lot of stuff doesn't get through to it. A lot of noise issues are alleviated. That's why building anything that goes in space is difficult, because of all the noise issues, the cosmic rays, all different types of radiation that can happen. Okay. All right, so all of our digital circuits, the input terminals of the digital circuits, they basically accept binary signals that are within the allowable range. So again, in this particular case, our ones have to be between 2 and 3 volts. Our zeros have to be between 0 and 1 volt. They might be able to go a little bit higher here. That's possible, or a little bit lower, but this is generally what's considered to be, absolutely acceptable. And the output of the terminals, or the output of that gate that we're using, the binary signal is also going to fall between these ranges too. So again, the intermediate region only happens when there's a transition in a state. So when I'm going from a 0 to a 1 or a 1 to a 0, that's the only time that's going to happen. Okay? So all of our computing or control signals can be operated on by passing those binary signals through a various series of combinational gates, right? So I take some inputs, I put it into an AND gate, and that might go to an OR gate, and that might go to an XOR gate or something. Each time it goes through these gates, that output signal is always going to be, again, within these specifications, right? Now, again, there's a couple things to consider. What if I have an output of one gate going into many other gates? Then we might have a loading issue, right? We might have to take that signal and we might have to buffer it up to kind of go in there. These are just things we'll have to do. Now, again, depending on how we design our circuits, a lot of software does that work for us. It'll make those checks and tell us whether or not we need to do that. So again, just like with analog circuits, you guys, I believe you guys did your analog project at some point in electronics 1 or 2. You can't just arbitrarily just connect things and don't expect there to be some kind of impact, right? So again, with digital logic, we have some flexibility there. I can connect, maybe 4 gates to one output of a gate and not really worry too much. But with an analog circuit, just connecting something to the output of an analog circuit or something else to the output could change its characteristics if it's not designed correctly. Okay, so again, this is another reason we like digital circuits. Again, noise margins and these loading issues. Okay, so these are basically the gates we use the most often below. I mean, there's one missing here, but I think I'll review it again anyway. So these are these graphical symbols, or the accepted graphical symbols of our gates. We can see the AND gate, the OR gate, and the NOT gate. So again, if we put in any input, as long as they're valid inputs, that being a 0 or a 1, on either the X and Y inputs, we'll get some proper valid output, such as the Z or the X prime. So again, each gate is made up of a series of transistors, and depending on the gate you have, that depends on how many transistors we get. Now, there are some limitations with the way we build transistors now. We can only build transistors on a single plane, and then we can wire them up on multiple planes. So whenever you look at an integrated circuit, if you look at a cross-sectional area, you'll see the transistors at the bottom and many layers of interconnect on the top. So this kind of limits our ability to build large circuits, since we can only build on a plane. And there's kind of a catch-22 when we do this. The more circuits we put down on a chip, the larger our chip gets. The problem, though, is the larger our chip gets, the slower our chip gets, because the wiring distance of the components gets larger, so it takes time for the wires to get, or the signals to get where they have to go. So we can't just make larger, faster chips. It doesn't really work. There's kind of a sweet spot, so to speak, where the size of the chip and the length of the wires kind of just works out. So this is why we don't have very, very large circuits in some cases. Now, again, this can be mitigated by building our circuit kind of in little sequences or chunks where information moves from one part of the chip to another. So all the signals kind of stay localized. We just kind of move the information around over time. And this is something we do with CPUs, how we build them. But we can't just make them, just ridiculously large and expect them to kind of work fast. That's something that kind of goes against it. So again, just keep that in mind. We do have some play with this right now, though. I don't know if people have, listened to the news about technology, but something we have been doing that's been reducing the size of memory chips is called wafer stacking. So we can take individual chips and we can stack them on top of each other. And we basically solder them together. So there's a place where a signal can actually go through the chip, or we can provide a signal to like the bottom of the chip and the top of the chip so we can stack them together. It's relatively new technology and it has its limitations, but it's definitely being used in memory chips to cut down on the amount of space needed. So if you've purchased a solid state drive before, it'll say something like it's got some 3D NAND chip or something in it, it might say. That's a stacked memory chip. And it allows us to make the components much cheaper. So rather than you buying 8 chips for the memory for your device, you only need to buy 1. And that's a huge savings in terms of, the packaging and the board space and the soldering and all those kinds of things. So it can lead us to more savings. But there can also be other problems too. Heat dissipation is also another issue. So there's a lot of engineering challenges in this. Okay. Now it's possible for these logic gates and or an XOR gates to have more than 2 inputs. Now, I didn't show you an XOR gate before, but it's pretty much looks like an OR gate, but just like a big curve in the front. I think I have some pictures after. So in this particular case, the circuits scale up pretty much the same way. So for a 3-input AND gate responds with a 1 if all the inputs are 1. 4-input OR gate, for example, responds with a logic 1 if any of the inputs are 1. Again, these can be easily scaled up, right? I can take the output of an OR gate, the output of another OR gate, OR it together, and it's like I ORed all the original inputs together, right? We can only do that with AND, OR, and XOR. The other gates, NAND and NOR, that doesn't work so well. We have to do kind of a different Boolean calculation to find the proper result. However, in practice, there's usually no more than 3 inputs used, as this slows down the gates. Now, again, if you do have a gate that has 4 inputs, and we do the design in software, eventually that 4-input gate is going to be reduced down to some version of a gate that only uses 3 inputs, right? It might use multiple gates and connect it together appropriately. But we don't usually go more than 3. There's, again, technology limitations here. I should say current technology limitations. Will they ever be able to solve this in the future? Who's to say? It all depends on what we can build and how small we can build it. So again, here's just our simple gates here. So our inverter gate. So there's an inverter here and a buffer. Now they look kind of the same. So a buffer just takes X and brings it to F, whereas an inverter obviously takes X and inverts it and brings it to F. The difference here is the little bubble we see here. And whenever we see the bubble, it means the signal is being inverted. Okay, so do keep that in mind. It's possible, I suppose, you could draw an inverter just by putting a bubble somewhere in your schematic, but if you do, we usually put it before another gate or immediately after that gate. Here, the accepted schematic for an inverter is the little triangle in front with the circle. Yes, we will be using Logisim in this course, definitely. That's where you're going to be doing all of your digital design. Okay, so again, just to let you know, so why do we use a buffer in the first place anyway? Since it doesn't change X, what it does do, it does improve the signal integrity of X. So again, if X is connected to a lot of things, or is going to be connected to a lot of things, those things are going to somehow weigh down X so that X isn't going to transition as quickly. It's going to load it down. So what we have to do is probably take X and run it through a buffer here. And the buffer is actually, one thing we don't note here is we can make buffers of different sizes. So they have an ability to drive more and more signals. The transistors get larger, but it allows us to kind of ensure that we do meet the specification of the circuit in terms of speed, for example. So a buffer just really only requires 2 transistors. So it is the smallest, or I'm sorry, an inverter requires 2 transistors. A buffer actually requires 4 because it's 2 inverters back to back. But it is necessary to kind of accommodate for situations where our signal is being loaded down too much. A good example of this, and you've probably seen this before, well, maybe you have, again, technology changes so often, it's kind of funny. In your house, if you used incandescent bulbs and you put too many bulbs on a circuit, you would notice whenever you turn on one bulb, the other bulb kind of dims. And that's kind of a good example of loading, right? It's taking more current away from that other bulb. Now, if you guys are using LED lighting, you might not even notice that because LED lights don't use as much power as incandescent lights do. The same thing could be said, well, what if you connect a vacuum cleaner, though, to that same circuit with a light? Then you might actually see it, because vacuum cleaners do use quite a bit of power. So they often will dim lights. Or another thing you might have noticed is when the air conditioner goes on in your home, maybe some lights dim, right? Same idea. It means your circuit is being loaded down. So a buffer does improve that. So we don't typically put buffers in ourselves. Our software does it before our circuit is built. It's like one of those little checks and balances it does. Okay, the OR gate and the NOR gate, well, I think you guys remember what the function of OR and NOR is. What I really want to get to here is that an OR requires 6 transistors, where a NOR gate only requires 4. So we often build our circuits using NOR gates as opposed to OR gates. And another thing you might remember from DLD1 is we often try to change our circuit, our whole circuit, and just change it into NOR or NAND gates. Kind of made sense. Question here, so how does a buffer stop it from getting loaded down? Well, a buffer is powered. So this circuit is being powered. So again, if this X is, here, let me just use the whiteboard here for a second. Let's assume this is my ideal transition. So here's my input signal. Okay, here we go. Sorry, where's my mouse? There it is. Of course, one second. Technology. For some reason, it doesn't think I want to use my pen right now. Okay, here we go. So here's my signal. Let's see, do I have my little pointer? Where are you, little pointer? Okay, great. Let me just erase that. Here's my signal transition time. So, okay, it's not really in that direction, but I want my signal to change as quickly as possible. But if it's being loaded down, it could transition more like this. Okay, so we can see it's taking a longer time for it to go from a 0 to a 1. So if I put this through a buffer, sorry, it's a little bit on an angle, I guess my arm isn't really aligned. The buffer is only going to switch. The buffer is going to switch basically when this thing reaches a certain point. So it's going to end up going faster, right? Remember, the buffer is only going to switch when it hits about here. So it's going to switch from a 1 to a 0. So that's how a buffer can kind of improve slow circuit performance if it's being loaded down. Now, if the circuit isn't being loaded down, it's going to transition faster. So a faster transitioning circuit going into a buffer is going to work better if you have the things behind the buffer, assuming it's a larger buffer, you know, where it can kind of handle it. The only downside to this is that I need a buffer and it might have to be larger, so the circuit gets bigger. So this is kind of why we want to avoid these types of situations. Okay, it's all about compromise. Okay, so again, how does it help with the response time with respect to delays? A slow circuit, again, I don't know why I can't see my pointer. There we go again. A slow circuit takes time to go up, right? So anything after this circuit is going to take time to respond to it. But if the circuit responds quicker, right? So here I got my 1, let's say roughly about here. Here I got my 1 roughly about here, even though they started at the same point to do the transition. So a slow rising circuit can slow down all the circuits after it, whereas a quick rising circuit, the other circuits respond faster. But again, it comes at a compromise. If I put in a buffer, the circuit gets bigger. So we're always trying to build our circuit with the smallest physical gates possible and only put in larger buffer circuits when we need to. And again, that's what the software does for us. Because if I start putting in just arbitrary buffers all over the place, my circuit's going to get bigger and I don't have room for other things. And that's one of our limitations. Okay, so back to our NAND and NOR. So again, functionally, you know, this one is just an inverse of the other one, but we want to try to build our designs with as many NOR gates as possible because it's only 4 transistors. Now, when it comes to NAND gates, same thing. We have AND and NAND. An AND gate requires 6 transistors, where a NAND gate only requires 4. And what's nice about a NAND gate is it actually operates slightly faster than a NOR gate. So if, whenever possible, we want to have our Boolean expressions expressed in terms of NAND gates, it operates faster. Again, 6 transistors, it's bigger and it takes longer for the circuits to go through. What an AND gate is essentially a NAND gate with an inverter after it. That's what it is. So why do we want to invert the signal if we don't have to? If we can reduce the logic down, it makes sense. Okay, so I know we like to see things in terms of AND and OR, but when it comes down to building things, it's better to go the other way. And this is why we spent so much time talking about NAND and NOR gates in DLD1. Now, as far as exclusive OR goes, this is probably one of the most useful gates there is. Exclusive OR, exclusive NOR, is a great way to determine if two signals are equal or not equal. It's a very fast way of doing it. The problem is it's computationally large, right? You basically have to build it like this. We use it so often, we actually have a symbol for it, but we don't have a way to do it fast. So either one requires 12 transistors. So this gate is quite large, and it is slower, but it's extremely useful. Okay, so it comes up often. If I want to compare two numbers, it's likely your circuit is using an XOR gate to do that. It's one of the fastest ways. We can do it in parallel, just run the output through a bunch of XOR gates or XNOR gates, and we just look to see, we AND all the results, or we OR all the results, I should say, and if it's a 0, it means it's equal. It's very simple. Very, very easy to build, very fast. Oh, I'm not going to go over gate conversions. There's no fast way to do that. We spent quite a bit on it. Again, if you guys want to go back, I think you can find that stuff on my website. All those slides are still there for DLD1. You guys can easily find it. We're not going to be doing that here. We're not doing any implementations, okay? I'm not going to, take marks off you because you used an OR gate instead of a NOR gate. I'm just telling you that's the nature of the business, in the sense of we want the circuits to be as compact as possible. Now, do keep in mind, from the perspective of us as designers, we don't normally do any of this work anymore. We used to do this a long time ago. And I think I told you a story about this many years ago. Steve Wozniak and Steve Jobs, they were looking for work again before they were, they started Apple. And one of the jobs they had was reducing circuit sizes for Atari. So Atari would give them a schematic and say, okay, reduce the number of chips here. And what they would essentially do is this Boolean logic reduction, change all the AND and OR gates to NOR gates and things like that, right? Or NAND gates. That's how they made the circuits smaller. It's just that simple. They just applied all these reduction techniques. The thing is, we didn't have computers back then to do that work, so you had to do it as a human. Now, if you guys were to design something and you were to sit there and put in AND and OR gates and all these kinds of things, the software is eventually going to go through all that and reduce it down as much as it can anyway. So we don't have to do that work anymore. Now, I'm not opposed to that type of stuff because I know it's a lot of work. It's easy to do the work. And in the end, the time it takes for the computer to do that optimization is usually quite small, and it doesn't impact the performance of the chip. It's not like, we're software. If you use a high-level language, you're going to end up getting slow code. It's just part of the way it works. But using a high-level circuit design tool that does a lot of work reducing the circuit for you does not end up making a slow circuit, right? If anything, it makes a faster circuit, because once that step is done, it's done. Whereas with software, you're always running, potentially slow code over and over again. So I'm certainly an advocate for software optimization, but not, having humans do, circuit optimization. These circuits get far too large that no human can kind of do this kind of work. There's too many scenarios. Okay, so another thing I mentioned before in DLD1 was the idea of tri-state gates. So again, we can have outputs on our circuit. We either have 0 and 1. Well, tri-state gates basically bring in this ability for our circuit not to drive anything at all. So we actually have the third state, the high impedance state. So I can make it so my circuit doesn't output anything at all. And this is very useful if I want to share a wire between multiple circuits. And this becomes very useful, especially in CPUs, because we have buses. Buses are a collection of signals. So I might have an 8-bit bus, which is just 8 separate wires. But what's going to be on that bus? Is it going to be the output from circuit A, circuit B, or circuit C? So tri-states make this easier to do. Otherwise, I would need a multiplexer that would select, okay, does A, B, or C, or D, perhaps, go to this output? Multiplexers get large as you increase the number of inputs. They're fast, don't get me wrong, but they get large, and that can kind of, have a cost on your circuit. So tri-states are kind of a way of solving that. Now, they have their own problems too, mind you, but you know, again, circuit design is all about compromise. So a basic tri-state, so here, basically a tri-state looks like a buffer, right? But we have this little control line, and that's how we know it's a tri-state. So normally A would just go through this buffer, so the output of Y would be equal to A if C is 1, for example. But if C is 0, now Y is high impedance, so it doesn't matter what A is. A will never be passed out. Now, what makes it useful is if I have another circuit up here, let's say B is going and it's connecting here as well, I would switch between either A or B goes to Y. And that's where it's useful. It doesn't scale exponentially like a multiplexer does. So it's got its benefits for that. So we often use this in traditional CPU design. This is how we have different components talk on these buses. And we'll see that a little later. Okay, another part we often use in any digital logic is a decoder. Decoder is a very useful tool. So essentially a decoder is, again, sorry about the quality of the photograph here, but you know, basically it generates all of our min terms for us. So if I give it any binary code, input A, B, C, so we can see here on our truth table here, here's A, B, C. Whatever code I put in that's interpreted as binary, only one of those outputs is a 1. So if my input code is 100, which is 4, if I interpret this correctly, only 04 will be a 1 and all others will be a 0. So decoders are extremely useful for this task. Where is the output going to go eventually? It can go to another circuit that enables something else, right? So having that signal of 04, for example, let's say that goes to another circuit that controls another part of my design. This device kind of did that for me. So as long as I put in that pattern, if the number is greater than 4, or sorry, if the number is only 4, then only that circuit's going to turn on, where all the other circuits turn off. It's very useful in this particular area. Okay, it is possible to have decoders. They're traditionally called N to M line decoders. So whatever N is, M is going to be 2 to the N. Now it doesn't have to be 8, for example. It could be 6. What's important is it never goes greater than 2 to the N. So it's never more than 8. It's possible to have fewer lines, and our software might optimize it out if I don't have. For example, if I don't have 05 connected to something, it might change the internal circuit here and remove all the circuit necessary to drive 05, and therefore make our circuit smaller. Now, again, I'm kind of alluding to, you know, FPGAs, for example, where we do all this stuff internally. Of course, you can still go out and buy a discrete 3 to 8 line decoder and use that. That's possible as well. So again, decoders are very useful. We use these heavily in memory design to figure out, you know, well, what part of the memory are we actually trying to read out? And I'll talk about that more in chapter 3. Okay. Again, here's another example of a larger decoder. Here is a 4 to 10 line decoder. Now that doesn't usually make sense. 4 to 10, it usually uses 4 to 16. But in this particular case, we're using it as a binary coded decimal input. So with binary coded decimal, only my first 10 states are important. The rest I could just ignore. So in this particular case, this is going to be a smaller design than 4 to 16 line decoder. So here's my output. So whatever BCD number I put in here, the corresponding O line will be activated. And if we look at these outputs here, we can see either a bubble here on the output, or we see a little line on top of the O here. This means active low. So in this particular case, only one of these outputs is going to be a 0, while all of the others are always a 1. So here's my truth table with all 16 possibilities. And when I go above 10, or above 9, I should say, the outputs are all 1s because there is no O10 and O11 and O whatever, right? Now, in case there's another possibility, decoders can have enable lines on them. So only if my enable line is asserted will one of these outputs be 0 in this case, whereas if the enable is not inserted, all the outputs will be inactive or high. So we have to kind of be careful when we look at decoders how these things are specified. Is the enable line, is it active low, for example, or is it active high where there's not a line on top, or is the output active low, or is it active high? There's no proper language, I should say, in terms of naming it. You just kind of have to read the specs and be aware of it. Again, here they put a bubble here to kind of say that it's active, low, enable, but some people might get confused by this being having a line on top and this being a bubble. So which one is it, right? You just have to be quite clear and know. Okay. Again, I'm as clear as I can possibly be in the assignments. I'll state that it's active high input or active low output or something like that, right? But not every book or picture is that clear. Okay, so in this particular case, I find this a little confusing myself. Do I look at the symbol or do I look at the wording? Right? Which one is it? Now, if I didn't know any better, I'd say, well, this is being inverted, but now this is is this being labeled correctly? Like, again, I'm just not sure. So I'll be more clear myself. I just want to show you like this particular example where it might be a little ambiguous. So you do have to read the wording. Oh, shoot, I just realized it's 2:30. Okay. All right, I'll give you guys a break. Inverted generally means active low, but then when they label this here, you know, again, that's the kind of problem I have. But yes. Okay, so I'll give you guys a 10-minute break here, and then I'll start up at 2:40. All right, so I'll just put my system in away mode here, and yeah, go whatever. Get a coffee, get a drink, go get your waffles or whatever it was. What was it? Egos. There it was. All right. See you guys soon. Okay, I'm back and talking. Okay, so we'll continue here, probably go until about 3:50. All right, okay, so I was just talking about decoders. So again, we use decoders quite often in this particular design, CPUs anyway, and systems that support them. Next, we have encoders. Now, I have to say encoders are a device not often used in most circuit design itself because it's very difficult to get the inputs to align correctly. So essentially an encoder is an absolute opposite of a decoder. You give it the same outputs a decoder would have and it would give you the same inputs that you would have given the decoder. The problem with this is, can you guarantee in the input sequence that that in this particular case that only D1 is only 1 and all the other ones are 0, right? Is that even possible? So the simplest circuit to build would be, for example, building X, Y, and Z such as this. But at the moment you deviate from any of these patterns, if just, there's just a 1 somewhere else, it just doesn't work, right? And again, the academic sense of saying, okay, encoders exist, yes, but we rarely ever use them as you've seen them here. What often happens is we have something called a priority encoder, which works very simply like an encoder, except it's more interested in where is the first one located. And in that situation, then we don't end up with those ambiguities. So in this particular case, we have the case that's just a 4-bit. Where is that first one located? Oh, the first one is at D0, so my output is 0. Or in this particular case, the first one is located at D3, so my output is 3. Now, because there is the possibility of us having all inputs 0 or nothing being active, we have to have some type of valid line that tells us of whether or not our position is even correct. So I use priority encoders quite a bit. And in fact, a priority encoder is actually used by a floating point system to do normalization. It's basically, we could use the priority encoder to say, where is that first 1 in our number? And is it in position 1? And if it's not in the right position, then we either shift left or right, or we're able just to basically determine how much we need to shift it by how many powers of 2, so to speak, right? So we use priority encoders quite a bit. Now, will we use any of these in this class? It's not likely, but again, I just want you to know about their particular uses. So I've often used priority encoders, but never an encoder on its own. Next, of course, it wouldn't be a review unless we had something on multiplexers. So again, multiplexers are a wonderful tool. Basically, this is our decision-making tool. It doesn't make the decision so much, but it dispatches them in the sense of it basically decides where information is going to flow. So we can decide. So in this particular case, we can see this is just a standard multiplexer. The idea is you have some select bits here that passes I to some output Z. So it's either I0, I1, or up to IN, it looks like over here. Now, if we apply it in some case, then multiplexers can be applied in many different ways. It's usually we say something like 4-to-1 mux. So here we have 4 sets of data, and one of these sets of data is going to go to Z. But you'll notice Z is 2 bits. So this is a 2-bit 4-to-1 multiplexer where our inputs are 2 bits, and one of these sets of 2 bits goes to Z depending on the selection pins S. So this is very important in our digital design because we have to kind of say, okay, well, I did a computation here, I did a computation here. Which one moves onward? Right? So we'll have some kind of circuit will decide which one is going to move on. The multiplexer actually does the work of kind of moving that data through. Now, again, this could be replaced with tri-state gates, but again, there's some little issues there. Multiplexers scale exponentially, so every time I add another select bit here, I'm basically doubling the number of input bits, which doubles the size of the circuit internally. They don't scale very well, but they do operate very fast. Whereas tri-state gates, they scale well, it's only linear, but because you have one circuit taking over driving a wire as opposed to another circuit, and they don't exactly switch at the exact times, there is sometimes capacitance issues there which slow down its switching time. So we don't really use those, we don't really use tri-state gates in high-speed design because, well, we're trying to get the most out of the design in terms of performance, not necessarily space. So again, it depends on what our objective is. The D latch, yes, okay, I just want to make sure I'm getting my terminology correct. I often confuse latch with flip-flop when I'm talking, so bear with me. So the latch is a transparent latch, basically. Just again, another review of another part we use. Whenever D is applied to an input here, it only passes through to Q if enable is, well, active. Okay. We call it a transparent latch typically because even if enable is on and D changes, you're going to see that change on Q. So in a sense, it's like, you know, it's just the information is going straight through, or it's transparent, is where it gets its terminology from. Okay, we don't typically design with D latches themselves. These came up during analog designing. Again, historically, when we were building digital circuits, we always wanted them to be small because transistors were expensive. Now transistors are small and quite cheap. We're more interested in performance and reliability and testability and verification. Do we know the circuit's going to work before we build it? So with those in mind, we progressed to the positive edge triggered D flip-flop, or I should say the D flip-flop, which is edge triggered. Now it could be positive or negative, regardless, they're essentially the same. Now again, it's just a review of them, but this only captures data on the transition of the enable line, which now becomes the clock line. So this is far better for synchronous design. We definitely need this. We can't do synchronous design with D latches. We do need D flip-flops. Now D flip-flops are built with 2 D latches with opposite clocks. So if we put them together, one becomes the master, one becomes the slave, and we essentially build that flip-flop. Now this does come at a cost. Again, a standard D flip-flop with no enable lines, just having the D and the clock input and, you know, maybe the Q and Q bar output, that's 24 transistors on its own. So it comes with a cost. They're rather large, but they're very reliable in that sense that we can do our digital design with it and generally not have problems. Again, if I go back to the early 80s, we didn't use D flip-flops to build microprocessors and circuits. We used other little tricks. And again, those tricks worked as long as the device was in spec. For example, you couldn't take a CPU from that era and just clock it to like very low frequency to save power. It wouldn't work. It would fail because it was designed to operate within a certain clock speed. If you went over it, obviously the circuit would fail because it wouldn't, you know, perform its calculations correctly. But if you clocked it too slow, it would also fail because there was a lot of self-timed circuits in there to preserve, you know, register values, which weren't registers at all. They were, you know, some bizarre, you know, self-timed device that worked at a particular frequency, but nothing less. So again, we don't do design like that anymore where those things are that specific. If you build a design with D flip-flops, you can effectively set the clock to 0 and the circuit will stop. And the moment you turn the clock back on, it will work. And this is certainly something we like for lower power designs where we can just do that. So as long as all of our circuit components are static, in other words, no DRAM, which again, if you guys don't remember, I'll talk about later, but you can basically pause the circuit indefinitely. As long as power is applied, it'll work just fine. Okay, those are our flip-flops. So there are some limitations to flip-flops in the sense of how we use them. There's 2 things we have to keep track of when we're building them. There is the setup time and the hold time. So these are pretty important things. Now, again, they won't really affect us per se, but you do have to be aware. With the setup time, we have to make sure our input is stable within so much time before our clock switches. Otherwise, there's a chance that when our clock switches, we're going to get this value here as opposed to this value here. That's what gets captured. And that would certainly be no good. The hold time works kind of, well, a little bit opposite, I suppose. How long do you have to keep the clock at a particular value for the flip-flop to grab onto the data? So if my clock is switching too quickly, and if I'm out of spec of the device, chances are I may not be able to catch that data in the first place. So we have to be very careful about that. Well, the nice thing about these rules is we can't often intentionally break the software again as it goes through and does all of its verification of our design, especially in FPGA. It'll ensure that this will never happen. It'll do whatever it has to do to ensure this doesn't happen. Okay, obviously we can't run the circuit too fast, but oh, and another thing I think I forgot to mention, that a negative edge flip-flop just has a bubble here to kind of imply that. So again, when we start getting into more elaborate devices, they just all become squares, as I said with the schematic. So it's always good to kind of label things here. Here you should say like D flip-flop or DFF or something like that. So when you're doing designs, if you're doing them by hand, but you know, if you're using Logisim, obviously it properly indicates what the parts are. Again, with flip-flops, we always have to be aware of what is their initial value on restart. And fortunately for us in simulation and Logisim, you're guaranteed that when you restart your design or you hit reset on it, it's always going to be 0. And that's by design, right? It's a simulation tool. But that's not necessarily the case in the real world. All flip-flops will, you know, when you power them on, they'll either be a 0 or 1, just like RAM. When you turn on a computer, it's the contents of RAM are anything, could be anything. So one of the first things it does is clearly, you know, it tries to zero it out or tries to figure out how much memory is there through a number of tests. In our particular case, we don't know what it's going to be. So we have to have some way of asserting flip-flops to a known state, because they generally run state machines, and a state machine in a bad state is not a good thing. So we might have what we call our direct inputs, which are asynchronous reset signals. So regardless of the state of data or clock, whenever I assert reset, in this particular case, it's active low, it doesn't matter what clock or D is, the output gets reset to 0. And sometimes we have an S on top with our input. Set means to set it, so to set it to a 1. An R is to set it to a 0. The S is to set it to a 1. Now again, this is asynchronous, so regardless of what the clock is, it'll reset the circuit. Now it's also possible to have synchronous resets, and basically a synchronous reset means no matter what data is, it'll be set to 0 when the clock switches, and that can be achieved just by putting an AND gate here with, you know, where one of the inputs is the reset line. So when reset is asserted, you know, the data would always be 0 when it goes through, for example. Again, depending on what you set your inputs to be, if they're bubbled or not. Asynchronous resets come with an additional cost, of course. There's more transistors in them. A synchronous reset, you know, you would only need like an AND gate there or something like that. But do keep in mind with synchronous resets, it takes a whole clock for the output to change. We have to wait for that clock to change before the output changes. So there's some benefit for using asynchronous as well. Again, it all depends on what your circuit does. We should always be aware that our circuits need to be reset. This is something you always need to do. But again, it only applies to flip-flops that really need to be reset. And again, these are usually the ones controlling our state machines. Most other flip-flops are kind of, you know, you could kind of ignore them because they don't control the data flow of your system. Again, I was just talking about state machines, and again, sorry, was there a question? I hear someone raised a hand or lowered a hand, but again, if you have a question, just type it in the chat. A state machine is basically a combination circuit combined with flip-flops. And we use our flip-flop, again, because if we used a latch, our flip-flop output, assuming this was a latch, the output would be passed through as long as the signal is high. Is that an inverter at the reset port of the D flip-flop? Yes, the bubble there implies that it's active low, which means when R is low, it gets reset, whereas when R is high, it doesn't. That would be the normal operation. Okay, so back to this one. If this was a latch, this signal would be passed through half of the clock time. So no matter what my calculation is, if it's done early, this would be passed through and it would cause an out of control or unstable feedback here, and we don't want that. So instead we use flip-flops here where the output of this circuit, this combinational circuit, is only passed once on every clock. And this is what makes sequential circuits work. The fact that the information is only passed at one instance back to the beginning. And the assumption is, of course, is that your clock switches faster than it would take for the path to go from the combinational circuit back to the flip-flop. Or else, again, this could be an uncontrolled feedback as well. So again, we don't use D latches in synchronous design normally, I should say. It's possible to use them. We usually use flip-flops only. Again, bigger cost, 24 transistors per bit, but you end up with a more reliable circuit that's easy to verify and make sure it works correctly. Again, there's no reason why, if you were to build a circuit today, and as long as you do your simulations and know that it works correctly, that it won't work. Okay, we have a whole bunch of software, a whole bunch of verification systems that can guarantee that chip is going to work, as long as you follow the proper procedure. Whereas with analog chips, it's usually more iterative procedure. You have to design one and put a bunch of test points in and do a number of things to kind of absolutely verify it's going to work. It's usually 1 or 2 or 3 times you have to kind of go through it. It's just the nature of the business, right? This is why we like digital. Okay. So flip-flops are great, obviously. But one flip-flop doesn't do very much. So we have to kind of group them together. And when we start grouping them together, we call them registers. So a register is basically a group of flip-flops which share the common clock. And for our purposes, we're always going to be using a common clock for all of our designs. It just simplifies the design. Of course, more higher-end digital design can do things with different clocks, but you have to be extremely careful on how it's done. It's also possible to do more than just have flip-flops. So we have counters, which not only are flip-flops that hold information, they can go through a predetermined sequence of binary states. So a counter doesn't just have to necessarily count upwards. It could count downwards, or it could count by 2 or by 3, or just something. It's just saying that it does change the sequence, is all the name implies. So a register is simply just a group of flip-flops, where a counter is a group of flip-flops along with some combinational gates that can perform some other kind of type of calculation. So, and we'll see those terms being used here. Okay, but often, yeah, you'll hear the term just a counter in its simplest state just means it's a register that, yeah, every time you put in a clock, it's incrementing by 1, for example. Again, we've seen these before. Now, again, this is just a review. Here's a basic idea of registers. Here's a 4-bit register combined together. Four flip-flops combined together to create a register. So again, here's our 4 separate flip-flops. We can see each corresponding bit of I goes in. So bit 0 goes in here, bit 1 comes out here, goes to bit 0 of A. All the clocks are connected, all the clears are connected, or the resets are connected. So this is a register. It's a 4-bit register. Now, again, it could be quite tedious here building these things manually all the time. So again, fortunately, Logisim has a way of doing this for us. We can put in a 4-bit register here. It has an element in its library for us. And with that, it has a write enable line. It has a reset line. No clear line, or sorry, a set line, but again, it's rare that we do that. It's again not saying that we couldn't, but it's just, this is a common part. So rather than building all of our designs like we would like this for 4 bits and whatever 8 bits or whatever, we can simply go in Logisim, insert this, and say it's 8 bits, and then it's done. So I always promote the use of using the n-bit mode in Logisim. So if you need 8 AND gates, and they're all operating on 1 bit of data or 1 word of data that's 8 bits, then tell it to put in an 8-bit AND gate. So there's only 1 AND gate on your screen, but it's 8 bits of data on each input. It just makes, again, designing easier for us as humans. This is a lot easier to interpret than this, for example. Although they're functionally equivalent, one is easier to, it's just easier to interpret. So again, we'll likely be using a lot of registers in our designs. I don't know if we'll be using a shift register too much. A shift register is usually a compromise on space for speed. So shift registers, for example, this register is essentially copying the input from some input SI, and at every clock it brings in 1 bit at a time and kind of feeds it through as long as enable is on. So here we're using flip-flops without an enable, and if our information is not to be moved through, or if the enable is not on, it just takes its previous input and just feeds it through. This is one possibility of a shift register. Okay, I was just kind of coming up with different designs, but again, shift registers are, again, a compromise, and a lot of information can be sent serially like this. So the connection between, let's say, this shift register and another shift register could be kilometers away. So if we send the information 1 bit at a time, it actually becomes quite reliable. In fact, I believe I discussed this at some point before, but mostly every transmission or any way we transmit data today is done serially, because it eliminates a lot of the noise problems that would normally affect parallel circuits. So Ethernet, for example, optical Ethernet or optical networking all does this. It sends 1 bit at a time down that wire, and the other end gets it, and it just assembles all these bytes for us in the end. I don't know if we're going to be using shift registers here per se, but you guys should be aware that it's really the leading method of sending information. Now, do keep in mind that the clock rates at which we send data serially in the technology we use is very high. So you'd say, well, why didn't we do this before, earlier on? We just couldn't generate clock rates that way, and we didn't have the ability to do wiring as well as we can now, to lower noise wiring and those particular things. So a lot of earlier technology is parallel transfers, but again, over great distances, that has a problem. So a lot of the technology in your computer today is serial. In fact, the only thing that's not being sent serially in your CPU or in your computer's motherboard is the connection between the CPU and RAM. That's the only thing that's parallel. Pretty much everything else is serially done. And it's done that way to minimize cost and increase performance. Now, again, when I say minimize cost, it's parts. We're not talking about design time. Design time is high. But parts, one wire is definitely cheaper than 8, and circuit boards get smaller and those types of things. Packaging gets smaller. We don't need as many input pins on a chip, but the design time is certainly greater. But parallel is logically an easy way to get started with. So we're going to be pretty much using parallel for all of our transfers in our designs. Okay, these slides just kind of explain how this information gets moved around here. Okay, so now when that comes to data transfer, again, the easiest way to transfer data, if this is my outputs of my circuit, I have 5 wires here, A being the most significant bit, so that's like the 2 to the 4 significance, B is 2 to the 3, and so on and so forth. If I want to send a signal from one circuit to another, I would just send out, well, here's my wires, A to E, and I connect it to another device. And whatever I have on A eventually goes to that device, whatever goes on B goes to that device, and so on and so forth. It's pretty straightforward. Again, it only becomes a problem when the circuit becomes very fast. That's where the situation comes in, and noise starts happening. But I'll leave that to another time. Whereas in a serial sense, if I wanted to send the same information out serially, I would have to send, okay, I'll send out, for example, this bit here. I send that out, then I send a 0, then I wait the next clock, I send a 1, then I send another 1, then I send a 0. So we can kind of see that process happening here. I think it's starting here actually, 0, 1. Actually, I don't even know if this correlates properly with this slide. It almost doesn't seem to, but again, I'm not going to, well, maybe I should take credit for this one. I took this out of a book, but I don't know if I actually ever checked it over. But in any case, it would take 5 clocks for it to get that information. Now, that's 5 at best. How does my receiver know when I sent the first one is a question I could ask. How does it know when I sent A initially? I might need another signal for it to realize that, like another signal that says, okay, this is the first bit. So that could add more wiring, or certainly a little bit more overhead. But again, in this case, I either have 5 wires, or in this case, I would have 2. It's always a compromise. And again, it always depends. How far away is the serial and receiver, or the transmitter and receiver as well? So those are some things to take into consideration. Okay. Again, typically we're only going to be doing data transfer in our components parallel, but we will be talking about serial communication, how we would have talked to our device from our computer, for example. So again, here's just, again, another idea of how serial communication works just over time. So in this particular case, I'm transferring information from shift register A to shift register B. Now again, and I'm taking whatever output from A and I'm just feeding it back, so it eventually goes back and it just replaces itself. But if you can imagine that there's a great distance between A and B, then we kind of see the advantages here. So as I start out, B has some value in it, whatever it is. Here's A, and after the first shift, everything is going right out this way. So the bit A, the bit here in bit 0 of A goes to bit 3 of B. And then this one goes to bit 3 of B, and this one goes to bit 3 of B. And after 4 cycles, B should be equal to A, right? Now again, the benefit here is I've only used 1 wire as opposed to 4. But that may not sound like a great savings, but let's assume this was a 32-bit number. It would have taken me 32 clocks to send the number, but rather than using 32 wires, I would have only used 1 wire, right? So it does have its advantages, but again, it's a compromise. Okay, we have to understand that. Circuit design is all about compromise. If you absolutely want the absolute best, it's going to cost you, or the best and the fastest, it's going to cost you the most money. And that can't necessarily be afforded. Okay. All right. So in our particular situation, I mentioned this before with tri-state buses. If we have multiple devices to connect, again, we can connect all these things through a multiplexer, but that becomes a problem because the multiplexer becomes very large. And in this particular case, I only have 4 devices. What if I have 8 devices or 16 devices? The multiplexer just grows, again, exponentially. So we kind of compromise and we use devices that have tri-state buses on it. So let's just assume I have these 3 devices here and a microprocessor. So if I want device 1 to be able to talk to the microprocessor, and the microprocessor is just listening to who's talking, I have to command device 1 to talk on the bus, but I also have to command device 2 and 3 not to talk on the bus. So all of these outputs have some kind of tri-state on it. So these would all go to high impedance on buses 2 or devices 2 and 3, but device 1 would go out of high impedance mode and actually drive this wire. So this whole bus here is being driven by device 1, and our microprocessor is seeing what's on that bus. Now, it is possible in some cases that device 2 and 3 could also be looking at what's on that bus. And that's fine. They can be, like, everyone can be listening on that bus, just like you guys are listening to me right now. No one else is talking. It's just me. I'm in command of the bus. I'm taking control over it, right? But as I'm sure you guys have seen on, TV or the internet, when people do these, meetings and everyone has a mic and you always hear someone making some noise in the background or someone's mic isn't on, it looks like they're having a confusing time sorting out how to arbitrate the audio channel, so to speak, right? So in this particular case, which device is talking has to be arbitrated by someone, and it's usually the microprocessor, for example. Okay, so the microprocessor would command which one of these devices to talk at once. Okay, so data busing is a normal way of having these devices connect. The nice part about data busing is if I have to connect devices 4 and 5, for example, there's no cost to the microprocessor. There's no cost to these other devices. We simply tap off the bus, and then we pull that information. Someone asks, is that the sole purpose of the microprocessor? No, the microprocessor is doing a lot of work, but it's usually in charge of the arbitration as well. And that's going to be done through addressing. So based on where the microprocessor grabs information, that's going to dictate who is talking on that bus at one time. Okay, so for example, I could arbitrate our video conference here by saying user 1 talk on the bus right now, or take control, and everyone else would turn off their mic. And then I would say, okay, user 2, take control, and everyone would turn off their mic except user 2, for example. Now, do keep in mind that the communication of me telling which one to talk is not on this bus. It's on a separate bus. So it's in effect, I would be using like the chat window to be telling who to chat or who to talk on the audio or the mic at once. So it does have to be arbitrated. Okay, just like anything else. Is there a component in the microprocessor that directs all of the processes it's doing simultaneously? It's usually not doing things simultaneously. In our simple design, it's not going to do things simultaneously. It's going to do one thing at a time. So what would be driving the other devices? In terms of telling them to talk, it's just the microprocessor. Now, what they're doing, they can't be active in that sense. They can be. Device 1 could also be receiving. In this particular case, it's just drawn that only device 1 talks and device 3 and device 2 talks. And it's totally possible the microprocessor could be the one talking on the bus, and all of these devices would be listening, but only one would be actively grabbing the information. So again, we'll talk about that. How does the microprocessor continuously switch the function it performs? Again, it's a circuit. So it's possible I could have one part of the circuit doing some work, another part of the circuit doing another work. So the CPU is driving wires and reading the signals. Well, it's usually doing one at a time. It could be driving the enable lines here all the time, but it's kind of saying, okay, am I reading this wire or am I writing to this wire? Yes, it can do that. Again, we'll see how that works. Again, this is more of our traditional CPU design approach. This is how we kind of started building them. And that's where we're kind of going with this class. I'm not going to talk about the way we do it today, certainly not, because today is about speed and performance. I'm just trying to get you guys to understand how it works in general right now, at least initially. Okay? So again, this is no different than if you're in a room talking with people. It's the same thing. If your medium is air, that you're using to talk to people, right? Your voice, goes through air. You can't have two people talking at once in close proximity. It's too difficult. You're going to miss something. You might catch some words here and there, but you're obviously going to be distracted by the other conversation. So we have to have some type of arbitration. Now, if this was a normal classroom, I would arbitrate things by, you have a question, you raise your hand, I point to you, and you talk. That's the arbitration. So we're going to have something similar to that, except it's usually based with addresses. So normally with microprocessors, we talk to these devices through memory addresses. So if I say I want to read from memory address something, some part of that memory address is going to imply the device, right? Or if I want to write to memory address or device 3, it would be some memory address with a 3 in it somewhere that would tell this one to take the information I'm giving. And these other two will ignore it because they know they're not device 3. Right? So this is kind of the approach we're going to take. So these common buses, they're by no means efficient, but they are functional. And this is if we don't have a lot of information to send back and forth, it certainly doesn't make much sense. Now, if I want to get extreme efficiency and extreme speed, I would certainly have a direct connection between device 1 and the microprocessor and device 2 and the microprocessor, like dedicated connections. But that would double or triple my wiring, and that's something I may not necessarily be able to afford. So again, this is a compromise using data busing. But again, we're using this as a discussion to figure out how these things are going to work. So the motherboard is only powering the CPU and allowing it to communicate with other components. Well, the CPU is the brain of the computer. So it is communicating. It is the one in charge of the communication with everything else. I'm not saying other devices can't get the attention of the CPU, and we'll talk about ways that happens. But primarily, the CPU is the brain of the computer. It is in charge of all the functions that are going on, for the most part. There's certainly other little housekeeping things that we have other stuff doing, but No, that's it. It's the one talking to everything else. Your hard disk just doesn't tell your computer something. You know, the computer tells the hard disk something, and then it tells the hard disk, okay, when you're done, let me know. So that's when the hard disk can kind of just maybe say, okay, something happened, just to let you know, but it's not actively taking control. The computer or the main CPU is in charge. Okay. All right. All right. So here's an example of a way that we can have multiple devices kind of pulling information off the data bus, and we're going to use realistic components here. So the 7400 series gates are basically just a bunch of discrete gates that offer particular functions. So the 74173, for example, is a tri-state 4-bit register. It has 2 input enables and 2 output enables. And again, why they offer 2 is basically so, we have different ways we can connect it to other components. So if I have 2 things that might need to connect to it, it avoids me having to put in an AND gate or an OR gate somewhere. So, but we're only going to be using it as one. So we'll short both of the inputs effectively. So here I can see these 3 individual devices. And in this particular example, I'm going to use the control of them to move information around. So here's this common bus. So one of these devices has to talk. So in order to command one of them to talk, I have to assert one of their output enables, and only one of their output enables can be on. So let's just say I assert the output enable of register A. This is an A, this is a B. I don't know if you can see it, there's a C here. So when this one is asserted, this one is going to be outputting on this bus. So it is driving the bus. So no one else can be driving the bus. If someone else tries to drive the bus, you're going to get bus contention. And it's not a good thing because, for example, let's say D, our data bus, this bit here is being driven with a 1 from this component, but if it's being driven with a 0 from this component, now I'm connecting a 1 and 0 on my circuit, and that's going to cause a power drain situation. Okay, and that's not good. So we want to avoid those situations. I'm not saying they don't happen for brief instances when we're switching between devices. We don't want it to happen for a long time. This is what makes our devices hot. This is where power consumption comes from, heat is generated when those situations happen. So it's not to say they don't happen. They happen for a very short amount of time, but we don't want it to prolong. So in this particular case, let's just say, register A is driving this bus and register B and C are not. Now, if I want to move information from register A to register B, I would have to turn on this input enable on B. So when this clock pulses and this enable is on, it's going to grab the information on this bus because it's wired into this circuit, and it's going to capture that information. And then before the next clock, I would turn off the input enable here. So on the next clock, it wouldn't grab that information, for example. Maybe I'll switch this one on so it grabs the next clock or something, right? So even though all the devices can potentially listen, we only command, well, typically only one of them to grab the information. And it does it within that clock time. So again, you can imagine other things on this bus as well. I mean, there could be a CPU or something or whatever, but I can't have more than one device talking on the bus, or we get into this situation where we do have a bus contention. And that's essentially, the bit is wrong or the information is wrong. And if the information is wrong, we can expect subsequent operations to be in error. Just the information is just wrong. Okay, again, my analogy, if 2 people are talking to you at once, it's certainly possible you could differentiate what they're saying, but it's more likely than not you're going to screw up the interpretation of what they're saying. And you're not going to get the whole picture, especially if they're giving you very specific information. For example, let's say they were both telling you a password to a system. Well, if you confuse just one of those pieces of information, the password isn't going to work. But if they're telling you a story, it's possible you could tune one out for a second and tune the other one out and still kind of get the story. Do you need to know what's inside of 74173? No, I'm just saying it's one of those kind of standard components. So if you were to build things with discrete components, I'm just saying that's what this one offers. There's a whole variety of these components. Again, keep in mind, The first computers were built using 7400 logic gates. Totally. Like they even built CPUs with 7400 logic gates. Someone asked a quick question. What is that you grounded? MR is that's the synchronous reset. So this, if that was asserted, this output would be grounded to, it would be set to 0 all the time, right? So I did state that over here. It's an asynchronous reset. So more than one device registers can be captured at the same time. Yes, just like when we're in class and I'm talking, it's not a one-on-one class. I could be talking to 100 people and they could all be hearing and understanding what I'm saying. The problem is if they start talking back at me at the same time, then I can't understand what they're saying. Do I need a clock edge to move the information onto the bus and another clock edge to read into the register? No, you can do it all in the same clock. Or you mean, can I have different clocks? No, you should. We're only going to be using one clock or one single clock in our design. So the output here outputs immediately. So the moment output enable is on, the output is just being driven. So we don't have to wait for the clock for the output to come out. But on the input, we need the clock that synchronizes when we grab the information, right? That's the way D flip-flops work. We can see the output anytime, but the input only captures on the clock edge. Okay, all right. All right, so again, here's just taking that idea and extending it a little bit further. Now I have an 8-bit data bus here. I have my different devices here. Again, output enable, input enable, they all get clocks. I drop the synchronous line. Here, the textbook uses a really thick line to describe a bus. So again, each device has an input enable and an output enable, an input enable and output enable. And that's kind of how we use to kind of send that information back and forth. So if we assert the input enable, it's going to grab the information on the bus on the next clock. And if we assert the output enable, it's driving the bus. So by using this method, we can connect any number of components together and simply just command which one is on the bus or which one is talking and who's going to be grabbing that information. And that's it. So it's a kind of a nice way of putting this all together. So our individual parts of our CPU will be connected this way, at least initially. Okay, now I have one slide left here. Just again, this is based again on the idea of a bidirectional bus. There's different ways of drawing this, and you'll see this in different schematics. So one way in the book, we see each individual bit on the bus being tapped off, but this is kind of time consuming to draw all this. And our brain doesn't like to see all that because it's not usually drawn so nicely, right? Especially if these buses get big, it takes up a lot of space. So we might use a thick picture here and like a very large arrow here or something. The arrow here, of course, means it's bidirectional. It's going both ways. And we'll see that here, right? Arrows both ways. So there's a 4 here implying it's a 4-bit bus. Or we might even see a more simplified method here where we just draw a wire and we indicate it's a bus by putting a slash through it and a number indicating the number of bits are on the bus. I mean, this is kind of the way I prefer just because it's easier to draw. And in fact, in some cases, we may not even tap the bus off like this to say it's going in, to 4 separate bits. I might just draw it in directly and just say, okay, that's just I/O, and I/O is assumed to be 4 bits. So in this particular case, this is still a register just like in the previous example, just like, these. However, I/O is being shared on one line. So the output enable here might also dictate which way is the data or the information flowing this way. So when I assert output enable, these become outputs and I'm driving the bus. But when I turn output enable off, then this becomes an input, and then I can assert input enable to capture that data on the next clock. Again, I would love to sit here and say schematics are standardized completely, but they're not. There's a lot of artistic license, so to speak, right? The oddest thing about electrical engineering is schematics are simply it's kind of like a functional design. It's not precise. It's just an idea of how things are connected. It doesn't necessarily imply how it's physically built. right? So there's some level of interpretation there. Whereas a mechanical drawing is quite clear. Here's what the object looks like. This is how it's built. This is the size of this or that, or this is the distance between 2 points. Here, it's just a kind of a guideline. So there's often, again, some artistic license on the way people draw schematics. We have some conventions typically. For example, what we'll see in this class is information always flows from left to right. That's one thing we'll often see, and we see that in a lot of the circuits we've seen in textbooks. Also, voltage levels are higher at the top than they are at the bottom. That's another thing we often see. But apart from that, I mean, schematics can look awful and still be functional, or they can look beautiful and still be functional. But it's just kind of a guideline for us. We don't really have a way of saying that what you see here is how it's actually built. Okay, all right. So I'm just going to do a quick poll here just to see how many people have created their iClicker account. Okay, and because I want to see if we can at least start the third lecture. I won't record that data, but I just want to see how it interacts, if we have problems, those types of things. And then I might let you guys go a little sooner. So it's looking like a lot of people have set this up, so it's a good test to see how this works. So make sure you have the app on your phone, make sure you guys are all ready. So I'm going to assume from the response here that you're ready to go. So you're all good. All right. Do I need to get it on my phone? You can run it directly on the website if you want. I'd like for some people to do that actually, so we can just see how long it takes from when I hit the button to go and everything like that. Again, this is very difficult for me to do on my own because of, I can't gauge, the different internet service providers and those types of issues. Okay, so 15 people are apparently sleeping. So do you have to sign in before the lecture? You just make sure you sign into the site and just be ready. Some of you may have seen, if you've signed in, it should say the class has started, because I did start the class. Can anyone verify that? Okay, so someone, yes, they can confirm it. Okay. Okay, not everyone has to confirm it. Thank you. All right. Okay, so let's do a little test here. Okay, so just bear with me while I get this started up. Okay, I'm just going to unshare my screen for a moment just so I can get everything ready. Okay, again, assuming you guys added the course. So if you don't have any courses listed, press the plus sign. It'll list the institutions you're on, pick University of Windsor, and then just type in microprocessors. We might be the only people using it. I really don't know. Okay, so let me share my screen again. Okay, so you guys should see my screen, correct? And you guys see the little bar down here at the bottom? Okay, so the moment I hit this little check mark here, it's going to start polling, and we're going to be able to answer items between A and E. In this particular case, I only have A and B. This is kind of just like a little quick slide just so that I can see how many people there are really actually here. I know Blackboard is telling me it's 82 are connected, including me, but I don't know how many are conscious right now, so let's just try this out. So if I click this button, you guys should see this picture of this screen on your devices. I'll just say multiple choice and go. Here we go. So it should appear, and wow, that worked out quite quickly. So you guys got the image quite quickly and you were able to respond very fast. So it was very quick. So it's working on the PC and the web browser. Anyone using phones, iPhones, Android, if you can chime in. It was simultaneous, worked on my PC, great. App worked on Android, Apple, good. Phone works, good. All is good. Okay. All right, so I can see I got 72 responses, and if I stop the poll, I can see what people answered if I want to see. All right, that's pretty good. Apparently someone entered D. Now, we will always have people who do this. Just keep that in mind. All right, let's try the next slide here. Okay, here's just a test to see if you guys can figure it out. Find the missing letters for this word. Again, I will start the multiple choice now. Now, the letters aren't necessarily in order, so you have to figure out what the word is with the missing letters. These will not be saved, no. This is just a test. So don't worry about getting it wrong. Again, I just want to see how well this all works. After this, I'm going to go on the online system and see how I can grab, the information out of it. So how many, I forgot to look, was it 75 people answered? So I'll typically wait for the most number of people to answer, then I'll stop the poll. So it's not going to be timed. Okay, so I'm not going to wait much longer here. So I'll stop the response here. And let's look at the results. And everyone picks C. Now you probably should know that the missing letters generates processor. Yes, Elon Musk. Okay, let's move on just one more. And then when I do move on, it'll put a star beside the next one, just again to let you guys know which was the proper one. So I'll review ours just to see what everyone said, right? And then I'll show you this to see what the actual answer is. Okay, next. Okay, let's start polling again. So I'm assuming from your responses that the picture comes up quite quickly on your devices, right? Just judging by how fast people respond. That's good. So I guess we all have good internet connections. Okay, so based on this, I'll start Wednesday's lecture again with the first question, are you here? Essentially as a prompt attendance. So I know you guys, maybe some of you walk in at like 10:05 or whatever, but we should really start on time. So it's good practice. Okay, it's apparently taking people a little bit of time to do this one. I will pretend I did not see that. Well, duh. All right, I guess we'll stop now. Now, again, please don't give each other the answer in general. It's not really helpful. So I'll stop it there. Again, let's look at the responses. You can see most people pick C again. And of course, the mystery word is computer. All right. And of course, it is C. It's funny the things our brains do. All right. So then, of course, that's memory devices. So I'm not going to start this slide, of course, but that was good to test that. So I'll end the class now, or I'll end this. Now, if you guys don't mind, I want to see what is it like when I hit end class with exit poll. Again, I can't see this information, so I'm just going to do this now. And if you guys can let me know what you see. So the class should end. It should kind of kick you out, bring you back to something. So what numbers did it show you, by the way? Did it give you a score number or anything like that? Just 100%, or it's just saying 100%, that's it? Okay, 3 out of 3 points. It actually says points. Okay, so the feedback is how well did you understand the class? I don't know if the 3 out of 3 points is you got 3 out of 3 questions correct, or right. So someone says I only got 2 out of 3, so you know you got it wrong. So I think that's the number of questions. I don't think that's necessarily the points because I changed the point system to be different. Let me just verify that. I did set it up so that you get 2. Okay. So, well, here's the situation. It doesn't know what's right yet, so it might say 3 points. But once I go in the system and assign the proper correct answer for each thing, then it might tell you something otherwise if you go and look at your responses later. Okay. All right, so I'll do that after, and maybe you guys can let me know on Wednesday if when you go in the system, maybe you can see your actual percentage. But as far as that goes, I'm going to stop here. We'll start chapter 3 on Wednesday, so I'll let you guys out 10 minutes early. Big deal. Yeah, I won't take these results as anything meaningful. Again, it's just to test it to see that it works. Okay. Yes, I'm going to start on Wednesday and I'll start recording because there doesn't appear to be anything that's stopping you guys from using this. I don't think there's any technological hurdle or anything like that. Again, for those of you, was there any clear indication there was some type of trial? Or do you just assume there's a trial? Overall, this is going to be 10% of our grade. So throughout the whole semester. Although I'm trying to get some confirmation to see if we can increase it, again, just to kind of spread things out. Okay. The lectures are recorded, and you can see that. So when you go into the online classes section, you click on like the little 3 bars, the menu option, you switch to recording, and you'll be able to see the recorded lectures. So you don't look at the current sessions, look at the recorded ones. All that stuff has been there, it's been recorded. It usually takes about 10, 15 minutes after I'm done a lecture for it to be registered on the system. Okay, all right, so if you guys have no other questions, I try not to use Blackboard too much because it's an absolute pain as an instructor to kind of put things on Blackboard. Whereas my other website, I can post things quite quickly. Again, if you have questions, please don't send me private chats because they don't really appear for very long. Someone was asking the best way to study for the class. There's no tests, so there's not much to study for. This is kind of like all open. So I'll just be giving out, again, projects, assignments, projects, labs, whatever you want to call them. So, I mean, you have access to all the information and you have access to me and the GAs. So really everyone should do quite well, assuming they want to do well. Yes, there are no tests because I can't verify a way of doing it. Was it always this way? Definitely not. But we're kind of forced into this situation. I mean, I'd rather have a test, but you know, it's again, there's too many ways to cheat, and it's not fair to everyone. Although I do expect that almost all of you are 100% honorable. I'm sure somewhere in the back of your head, you know someone who's not. And the moment I said that, a name came in mind. So if that's all, if you guys have any more questions, again, just I'll sit around here. Program the microprocessor. Again, we're going to be doing a lot of things with simulation. So you'll be sending me basically your code that I will run over here in a test environment. Like I can test your performance, but you will be writing your code and running it in a simulator. Unfortunately, you can't use the real boards because we simply don't have enough. I mean, if we had enough, you might be able to have taken them home, but we just don't have enough. They're actually rather expensive. They're almost $200 a piece. And yeah, we only have about 40. Is the course outlined on the website yet? No, because I don't have 100% confirmation on a couple things. The grading percentages is simply 100% projects right now, but it'll probably be 10% participation, 90% projects. So there's really not a whole lot to see there, unfortunately. Oh, the one thing I probably don't have is I usually have the intro slides posted there. It might have the ISBN numbers of the textbook, but I think most people have the textbook. And if you don't have the textbook, just ask someone in the class. There's apparently an electronic copy floating around. When is the well? It's funny that the GA asked me when is the GA office hour. I will be posting the GA emails on the website soon, and you guys can kind of figure out when you guys just want to contact him and email him. And again, the GA took the class about 2 years ago. He did very well in it, so he's pretty good at it. Okay, so if there's no other questions, let me just check. Someone sent me a few personal chat messages here again. If you guys can avoid that, that would be great. Okay, I already kind of answered those. Oh, here's someone else. Okay, someone just mentioned they have a co-op interview during class time. If that's the issue, just have co-op, someone from co-op email me telling me you weren't available during that window of time plus whatever travel time is, and I will certainly make sure that those don't count against you. I believe the 6th edition is the preferred version of the website. I did post the 5th and 4th edition as they're essentially the same book, with just minor differences in the end of chapter questions. Again, it's up to the GA if he wants to have a fixed time or not. But I mean, is anyone on a schedule right now? Does anyone know what date is? Is anyone wearing pants? Right. So does it really matter? Yes, I'm wearing pants. I'm always wearing pants. They might be pajama pants, but they're still pants. Yes, I'm wearing a shirt. You have to pay me extra if you don't want me to. All right. Okay, well, if there's no more questions, I will see you guys on Wednesday, where we'll just have our standard 1.5 hour class time, and that'll be it until the following Monday. So hopefully the whole clicker thing will work out just fine, but I'll verify that with, I'll try to download the results and make sure it all worked out. Okay, so if that's it, I will leave you guys to it. And I'll post the GA's email as well. He's saying just send me emails if you have any questions, but obviously you guys don't know how to contact him yet. So, all right, I'll see you guys on Wednesday. Have a good, well, 2 days. See you then.